By 2026, CPUs have been the backbone of every computer on Earth for over 50 years. But for a small category of problems, they've just been humiliated. A new kind of chip, one that doesn't use bits at all, has completed a calculation in minutes that the world's fastest supercomputer would need longer than the age of the universe to finish. Some benchmarks put it at over a million times faster. The catch? This chip can't even run a calculator app. And understanding why is way more interesting than the big number. Every CPU on the planet, no matter how advanced, works the same fundamental way. A bit is either a 0 or a 1, on or off. To solve a problem, the CPU has to check possibilities one at a time, or a few at a time if you throw more cores at it. For most software, that's completely fine. But there's a category of problems where the number of possibilities explodes so fast that no amount of extra cores or clock speed will ever catch up. Cracking large encryption keys, simulating how atoms bond in a new drug molecule, searching an unsorted list of billions of entries. These aren't slow problems for a CPU. They're problems that would still be running after the sun burns out. This is where claims like a million times faster come from. Google's Sycamore chip and their newer Willow chip both ran benchmark tasks, specifically designed to be brutal for classical computers and natural for quantum ones, and finished in minutes what would take a classical supercomputer longer than the universe has existed. But here's the part most headlines skip. That number applies to one specific cherry-picked benchmark, and this is where it gets almost funny. A QPU can't run Chrome. It can't run Excel. It can't even reliably add two normal numbers together better than the calculator on your phone. Qubits are extremely fragile. The smallest vibration, temperature change, or stray electromagnetic field collapses the superposition, a problem called decoherence. That's why quantum chips have to be cooled to near absolute zero, colder than deep space, inside refrigerators the size of a room. And even then, error rates are still high enough that most of a quantum computer's power right now goes into correcting its own mistakes, not doing useful work. So what's it actually useful for now? Three real areas. Cryptography, where Shor's algorithm, running on a large enough stable QPU, could eventually crack the RSA encryption that protects your bank, your passwords, basically the entire internet. Drug and materials discovery, where simulating how molecules actually behave quantum mechanically, is something classical computers are fundamentally bad at because molecules themselves behave quantum mechanically. And optimization problems, logistics, routing, financial portfolio modeling, where Grover's algorithm can search massive solution spaces dramatically faster than brute force classical search. And just like with any hardware revolution, the chip is only half the story. Nobody's going to rewrite their software from scratch to use one. This is exactly why companies like IBM, Google, and IonQ have built software bridges, Qiskit, Cirq, that let developers write in familiar languages and have the framework handle the translation into quantum circuits underneath. Without that bridge, quantum computing stays a physics lab curiosity instead of a usable tool. Right now, a quantum processing unit will not be replacing your CPU. They're deployed as specialized co-processors. You send a classical computer's hardest, most exponential subproblems over to the QPU, get an answer back, and the CPU handles everything else, including just running the operating system that lets you talk to the QPU in the first place. It's less CPU is dead and more we just found a wrench for a very specific, very stubborn bolt. The real race right now isn't about raw qubit count. It's about error correction. Every major lab is chasing logical qubits, where thousands of fragile physical qubits are combined and error corrected into one stable, reliable qubit. If that scales the way researchers hope over the next decade, we go from impressive lab demo to genuinely breaking encryption standards the entire internet still relies on, which is exactly why NIST has already started rolling out post-quantum encryption standards years before the threat even fully arrives. Also, if you like this video, you can consider subscribing to my channel.